All right. How you guys doing? Doing okay? So we have an exam in a week. Ready for that? Feeling okay? Maybe? Have you began homework 2? No? Yes? Some part way? For those of you who have started it, how does it feel? Feel all right? Maybe? Maybe not? Okay. Well, we're gonna talk about that on Tuesday for sure. That and homework 1. So that'll be a lot of problems for us to talk about. So if you do have something in particular you'd like to get clarity on, make sure you have a question kind of in mind. Stop me, or make sure that you call my attention to what wasn't clear. But my plan for the exam review will be to go through all that. That'll be Tuesday. So it'll be in your best interest to give this homework a good shot. See what you think of it in preparation for the exam. I will talk more about the exam when we have the review session on Tuesday. But typically, I have problems on it, like the homeworks. So I'm going to give partial credit if you had a good process, even if you got the wrong answer, right? So I'll explain more of that on Tuesday, but that's kind of my expectations at the moment. And then good chance on Tuesday, I probably won't have the entire exam ready. So if you ask me what's on it, I'll just be taking your tips. Be like, oh, you didn't want that? All right, we'll do that. No. But seriously, I do put these together after we've talked about it, so I can kind of get a feel for where we're at. Okay, so with that, today we're going to finish up our conversation about flocculation. So we talked about coagulation last time and began flocculation. I think we'll probably have some extra time after solving an example problem to essentially begin talking about granular filtration, which would be a material beginning for that will not be covered in this exam, will be covered later. But I'll just stop with a big picture overview, tell you a little bit about how granular filtration works, and so that when we begin talking about the technical aspects, you'll have some familiarity and we'll pick back up like that. All right, so with that, I'm going to get going. All right, so last time we left off talking about the mixing intensity for flocculation, and why mixing intensity was important, because we want the particles to be able to meet each other. Why do we care about that? As well, we want to know how fast this flocculation process is going to happen. So when we want to know K, how quickly will this thing happen? How big of a reactor do we need? How fast do we have to stir it? All of these pieces go into how fast we are causing particles to stick together and make them bigger. The whole point is making them bigger so that they settle faster when we take the next step into a sedimentation chamber. So we'll end up with 2 sedimentation chambers, quite typical. So just as a reminder, we've seen that graphic a few times where we have some sedimentation chamber, then we're going to send it through some coagulation, dosing. So we're going to add coagulant, then give it some time to do our flocculation, some more gentle mixing. And then we'll go into another sedimentation. So if this would be our first one, then typically we'll go into a second sedimentation. So the point is, we want to be able to design this reactor here. How much time do we need to give these about this mixing intensity, where our intensity itself is going to depend on the power that we're putting into the stirring, the volume of the thing we're trying to stir, and the dynamic viscosity of it. This becomes pretty intuitive that those are the pieces if you ever try stirring something, right? Try stirring a swimming pool. Well, if you sit on the side of the pool and kick your legs real hard, maybe you make waves throughout the whole pool and you get some stirring, right? But you're putting a lot of energy into it because it's a big volume. Try to stir a can of peanut butter and it's tough because it's viscous, right? Or honey or something. you can get a feel for this relationship just intuitively. And if we want to be highly technical about it, we can describe the mixing intensity as this gradient of how the difference in our velocity of some surface stirring the tank or some water passing by the wall of a tank. That difference as you go away from that surface, the drag forces bring it to zero. How sharp is that gradient out into solution? That's a good description of your mixing intensity. Okay, so all that to describe this parameter G, which will be one of the parameters going into K. So the G here, this is a per second unit. It's going to be per second because we'll have power in watts, and watts is a joules per second units. Dynamic viscosity, we will have, this is just a characteristic of our liquid. We have a table, a lookup table for the temperature dependence of the viscosity for water, and this will be in units of kilograms per meter second. Our volume then we should have in meters, and with all those pieces in place, we'll be good to go. This will be a per second time, or per second unit, which will ultimately, as you can see, if G is in per seconds and we need K, we talked about last time in a first order rate constant, well, K will be in per time, and there's a good chance that our equation for K, when we need to find it, will have something times G, right? That we can expect that because it's giving per time units. So maybe there's some other stuff, we'll see that in a second, but that's kind of what we can expect. Yeah? Sorry,
so in that diagram, is that a Y, like a variable, or is that like a formula?
Down here? Yeah. This is just, the way the book often draws clarifiers will be like this, where we would have water allowing settling here. You'll accumulate your sludge, and then typically you'll have some waste line to remove the sludge. So good question. And in fact, I'm going to jump to the start of this slide deck to kind of show you, this is how they're drawing it, right? So I'm just kind of copying the way they do it. And the reason they're doing that is because sometimes you will design them a little bit conically at the bottom to capture the sludge and let you just pump it out. It'll just be kind of a slurry at the bottom and just a slow flow rate. You can remove all these solids that you're accumulating. In practice, we've often talked about sedimentation basins as either rectangular or circular. And so just the drawing, keep in mind that's just the way they're drawing them. It's a good question. Okay. So most of the water would flow across, and then we take a small amount for sludge collection. We'll see this same diagram type and a very similar approach when we get to wastewater treatment, where again, we'll use gravity if we can, then we'll send it through some process. We'll swap out the coagulation and flocculation with growth of bacteria in order to perform a lot of removal of waste products. Bacteria are great for that. Then we'll want to clarify, and that's when we use the word clarifier more often as in wastewater, the water leaving by allowing these bacteria clumps to settle. So we'll see this again in a very similar format. We'll talk more about that in the future. Okay, so about this kinetics and about the rate at which our particles, it's a number concentration of particles, so we're going to use N for that. We've seen dc dt, it's no different than dn dt. I'm just using N because it's a number. It feels a little better that way. That's also the way our book does it. So if we have this as a first order decay reaction like we talked about, our reaction will look like this. dn dt equals negative k times n. That will be our reaction term. And of course, we could put that in some volume. So this will be first order decay, and that means the number of particles will decrease as the size increases. So again, last time we talked about this a little bit, gave you a little example. So if we imagine I draw 8 little particles in here, we send it through our process, and we end up, let's say, with 2 particles, each composed of 4 of these smaller particles. then what we would say, well, first of all, we can see visibly, I drew these a little bit larger because they're clumps of the smaller ones. If n initial is equal to 8 particles, and the volume here is just whatever circle I drew. Maybe we can imagine this is a spherical little 1 milliliter or 1 liter clump, right? So we could just say 8 particles per volume. And it went to 2 particles per volume. Right? Very intuitive when I write it out that way. The reason I'm making a big deal about this is because when we set up any sort of equation or solve a mass balance, it's going to be very good to keep in mind physically what's happening so we can understand how big these particles are growing and relate the physically what's happening to the theory of our mass balance. Okay? So when I say n over n naught for this example, what does that equal to? Yeah, and so what would the number be? What's that? Yeah, 0.25, 1 over 4, or 2 over 8. Okay, so this would be, if we just simply said, this is n, that would be 2 over our initial 8. That'll be 1/4 or 0.25. Okay, so that makes sense if we stop and think about it elaborately like that. And you know, as you see, it kind of stops you mid-tracks and be like, oh, okay. So if I say then there are 4 particles in each aggregate, another way to write that would be to say n naught over n equals 4. So the number of initial particles per volume per final particles per volume is 4 in this example, right? We could say 4 is the number of initial particles in each aggregate, or whatever language we want to use to describe that. So what I'm doing here is I'm guiding you on how to connect a word problem and how it might be written in a word problem. They might not even use the number 4. You could write 4. You could spell it out. But you still have the technical information to connect to the mass balance, right? So what I'm trying to do for you right now is guide you on how you would associate some problem written in written form to how to solve it out mathematically. So if I tell you we have 11.5 initial particles in each aggregate on average after this process, then you should be able to say, oh, okay, well, if we assume the volume is conserved on these particles when this change happens, we could then solve for the new diameter of the new particles. Okay, it'll be a little bit of geometry to do that because we have to go from a sphere of some diameter with a total volume. We're going to assume the new particles are also spheres somehow, just clumped, but we preserve the volume. Then we say, okay, we'll just do a new volume calculation based on that, based on the conservation of the volume, and then solve for a new diameter. And then we can solve for the settling velocity. Okay, so that's kind of where we're heading. And this is how the K here will matter, which again, as we'll talk about in a moment, this K will depend on a few things like the mixing intensity. Okay, does this make sense kind of where we're going? Question?
So when you're saying that you can then use a diameter for the settling velocity, but doesn't that, since the particles keep changing over time, doesn't that mean that the density of the particles keep changing? So wouldn't it, have an arbitrary settling velocity at like any given time?
It's a very good question. So in case you didn't hear it, the question is essentially, aren't the particles changing size this whole time as the process goes? So at any point, how do we know that they're the same size, right? Or density? Well, density should stay the same because that's going to be a mass per volume term. So we don't have any way that we're changing the mass per volume of these particles. So as they clump together, yes, the volume changes, but the mass changes correspondingly. So that's a one-to-one change. So the density is fine, but the size, yes, it will be continuously aggregating. So the way we'll treat these problems is to say, let's give it this amount of time for the process. We will achieve some average particle size after that process. And then we're going to assume no more coagulation, no more flocculation after that. However, in practice, great point, in practice, it won't follow this exactly. This is a good way to design something because it turns out that it's pretty reliable, but we would always try it out and do some empirical tests, meaning you just physically try it and see what happens and take some measurements to say, okay, at first it's settling about this speed, tracks pretty well with this type of sedimentation, but eventually as the particles are falling, there's more of them and they'll make some sort of blanket possibly. There's a few different classifications of types of sedimentation. I'm not going to trouble you all with it. I'm just elaborating because there's a good question here. There are perhaps other tools we could use, but mostly from empirically derived stuff to say, okay, now we've got blanket sedimentation or different things like that where it's like, okay, now the particles have this dense layer and they're not settling very fast because they're kind of pushing against each other. So there's an assortment of different dynamics that come into play. So it's a great question there. We're just mostly going to assume that we have discrete particle settling and they're going to stay that way for the purposes of our design. Okay, good on that? All right. So let's dive into this rate constant. So we have K, our rate constant for essentially particles meeting each other. So what drives the speed or the rate at which particles are meeting? Well, one is the mixing intensity, of course, but there's another factor that is, and we mentioned this last time, somebody was saying, well, how many particles are in there matters. So we also need to have something that describes the portion of the volume that has particles in it. So if in my 1 liter of water, there are 2 particles, that's a very low density of particles, unless the particles each were half a liter in size. If there are 2 particles at half a liter in size, well, they already met. They're sticking together because they have nowhere else to be. But if these particles are really small and there's only 2 of them, a very, very small portion of this volume is particles. So they're very unlikely to meet. So we have a term in here, in addition to the G, we have this omega term that's going to describe the portion of the water that we're looking at, that portion of that volume that is occupied by particles. Okay, and I'm kind of jumping ahead, but that's the flock volume. That's going to be a unitless feature because it's going to be a volume divided by a volume. It's going to be the volume of the particle. So perhaps unitless is not exactly correct. It'll be the volume of the particles in the water divided by the volume of the water. So it will come out looking unitless. Really, it's a volume concentration, which we never talked about being a thing. But it's how concentrated in terms of volume are the particles in here. And again, if you think about trying to put 2 tennis balls into my 1 liter bottle of water, that's a lot of volume that the tennis balls are occupying, and there's a very high chance that they're going to meet if there's any sort of mixing, right? In fact, they're probably going to try to float, and so they'll obviously meet. But if they were the same density of water, a tiny, tiny, tiny bit of mixing should do the trick, and they'll bump into each other. Okay, so let's take a look at this K. I'll stop being ahead of myself here talking about the flock volume. So K is a function of this alpha. This will be a collision efficiency term, times 4 times this omega, this flock volume. We'll come back to that. Times G, the mixing intensity. All that divided by pi. So we can see it probably has, this equation is coming from some pieces that are geometric in nature. this mixing intensity, that flock volume, and then this collision efficiency thing is coming from whether or not the particles are destabilized. So we talked about coagulation last time. If when the particles meet, they stiff arm each other and say, nope, I don't care, I've got the same charge as you, and I'm going to stay away. Well, every time they meet, nothing happens, the K is 0. So if our collision efficiency is 0 because they are completely stable in water with the stiff arm, right, the electrostatic repulsion, things like that, then this entire rate goes to 0 because they never stick when they meet. So this collision efficiency is the fraction of collisions of particles that end up creating a new single particle of two particles combined. So the fraction of the time that when they meet, they stick together. So if we've done our coagulation well, then this should be 1. Could never be more than 1 because you can't have 200% of the time when they meet, they make a particle. That doesn't make any sense. So this can only go from 0 to 1. And if we've done any destabilization, it should be above 0. So typically, if we have any rate at all, it should be somewhere above 0 and up to 1. So if we see a problem that says they are completely destabilized, this goes to 1, and we forget about it. Okay? If we say it's partially destabilized, well, maybe we have a fraction here, and we deal with that. It's very simple, though. It's just going to go straight into our term. And you see it has no units. It's just a proportion of collisions. Okay, so if 50% of the collisions yield a new particle, this is 0.5. Simple as that. Okay, then we have 4. Then this flock volume. Then G divided by theta. So then we need flock volume. And I've already gone ahead of myself, and we can see why it's a unitless. And we can also see we could calculate that, or we could find out the formula for that without even having the formula on your formula sheet. Okay? You will have it on your formula sheet. It'll be there. But so that you can understand what's happening and which particle volume do you use, are we using the initial ones or are we using the final ones? That kind of thing might be important, right? So when we have this, this equation here, it will be good to recognize where it's coming from. And the way we're going to solve this is because we're going to assume, we mentioned this earlier, I'm going to go ahead and write it up. We're going to assume that the volume is conserved. When we cause them to aggregate. So if we started with 10 particles with a volume of 1, and we make 2 particles out of those 10, we will have 2 particles, each with a volume of 5. Okay. So in our example a moment ago, if each one of these little guys was assigned a volume of 1, something, unit, then now we have 8 total volume and still 8 total volume. Okay? We changed the number, we didn't change the total volume. That's all I'm saying. So what that will mean is we can go ahead and count based on some known initial number of particles. It's going to be the most common scenario. Take the n naught here. That's the number concentration of particles. So that'll be particles per volume. And then if we calculate the volume of each one of those particles, we multiply that times the concentration, and we get our volume per volume result. So this will be, if we wanted to write it out, we would say the number of particles per volume that we're considering of the water times the volume of one particle. Okay, make sense? It's pretty straightforward. And so then we take the volume of one particle, volume of a sphere, would be pi times its diameter cubed divided by 6. Okay? So we've seen that before. That means that our equation becomes, for this flock volume, this will simply be n naught times pi times the diameter cubed divided by 6. Now, one thing to consider here is if we're going to do volume per volume, and we want it to be unitless because G is the only piece with units, we don't want to have a rate constant that says milliliters divided by cubic meter per second. That rate constant is going to be funky, and we're not going to know what to do with that. So we want to make sure this becomes unitless. So sometimes you'll have a particle size in micrometers, and maybe you have particles per milliliter, so we should probably convert everything to meters or some like term. Right? I don't really care as long as you correctly convert it to a like term. So on this equation in particular, watch for the units. We might end up with a situation where we have number per liter and the diameter of the particle in, I don't know, micrometers, right? And so then you need to convert from liters to meter cubed, probably, and from the micrometers to meters. That's what I would do. Okay? Yeah. All right. Good on that? Okay, so now at this point, we're basically just going to apply the mass balance stuff we talked about the last couple weeks to these particles and figure out how big they're growing. And essentially, we have all the pieces in place now. So here's an example problem. I'm going to give you some time to think about it. It's a pretty big problem, so it will take a bit of time. I'll step you through it like normal, but I'm going to give you probably 10 minutes at a time, so a little more time than normal, to see how far you can get with it, to test yourself. This is exactly like a question we could have on an exam. So you can think of it like an in-class quiz if you want, but this time you get to talk with each other and work with it and get my help. So use that as a tool. Do you have the memory of what to do about it with the mass balance side of things as you're working through putting the new pieces together? I will also give you the equations. We'll write them up. I think I might have them. No, but I'll write them up in a moment. The equations we just looked at. So you'll have those on hand. Okay, so let me read through the problem and get you going on that. So this is silt flocculation before sedimentation. So we had, in a previous problem that we solved, we had some silt particles, and we realized at the end of the day they were not settling fast enough after this rain event. So to improve their settling, these 0.01 millimeter silt particles are completely destabilized. Mentioned what that means already. If I can find my cursor here. By adding alum, that's that aluminum sulfate, and it's passed through one of two side-by-side well-mixed flocculation chambers. Draw your systems, guys. Always start with drawing your system. That will help. Okay, the chambers are cubic, with each dimension being 3.5 meters. They are mixed with paddle mixers that input 2.5 kilowatts of power into the water and into each chamber. The water entering the flocculation chamber contains 10 to the 5th particles per milliliter. And the question is, what is the average diameter of the aggregates leaving the chambers? Okay, we have a few other conversions here. So the flow rate was given from the previous example as 3 million gallons per day total. And we have that conversion rate there of 1 mgd is 0.0438 cubic meters per second. Also went ahead and got the dynamic viscosity of water for you here, in case you need that. As that was the 1.145 times 10 to the minus third kilograms per meter second. Okay, so draw your system and begin working towards setting up a mass balance that will let you use the rate to put in the stuff you need. I'll go ahead and write up the reminders. Actually, I'm just going to go ahead and flip to the next page. So I can write a few things for you, and then we'll have space to work everything out. All right, you're welcome to ask each other. You're welcome to ask me questions along the way. Again, I'm going to give you a little bit of time, and I'll write up a bit, talk to you a bit, and give you some more time.
joules per second or kilojoules per second?
The power?
Yeah.
The power should be in watts.
Watts.
Yeah. So I had a question, good one to go ahead and highlight for you. You have a value for power and the equation. See, this is the kind of thing you want to make sure you recall for an exam. This should be in watts. And you can remember that because the dynamic viscosity here is in units of kilograms, meters, and seconds. It's not in kilometers. It's not in, yeah, it is in kilograms, but newtons are also kilograms. That's where the newtons, joules, all that comes through. So power should always be watts. So you're going to have to do a conversion there. All right, so I'm going to check in with you here. I hear a lot of you working through some of the units, lots of unit conversions with this problem. So it kind of really makes you face all the different weird stuff that might happen. So we have power was given in kilowatts. We got to put that into watts. So multiply that by 1,000. We've got the equations written up here. The initial particle concentration is 10 to the 5th particles per milliliter. So it's 100,000 particles in each milliliter. But we need to know how many particles in each cubic meter if we're going to compare that to the volume of this, we just need the like numbers. So if we're going to take the particle size and convert that probably into meters, and then cubic meters for the volume of a particle, we got to convert this. So multiply by 1,000 to get from milliliters to liters, and then there's 1,000 liters in 1 cubic meter. So we should essentially raise that from 10 to the 5th to 10 to the 11th. So just add 6 to that. That should get us 10 to the 11th particles per cubic meter. Sometimes I just write a little p here for particles. Maybe just a number sign would do. Whatever you like to do there should be fine. Okay, so then there's two things that I think are worthwhile. First of all, what we were just doing is getting the units in order so we can put in the equations how we need them. So I also have the flow rate here. The other piece is drawing the system and understanding really what we need to do with it. So I will finish getting these numbers, and then I'll even work out these calculations and write the values that I got down. But what I'd like for you to do next is to figure out what are we doing with the mass balance here. And as you saw, I've drawn it up as water coming in, splitting into 2 directions, 2 different reactors, but these are identical reactors, and then coming back and merging, and that's our effluent. So what's coming in is the N naught, and do you expect this initial concentration to change when we split it into 2 directions? What's going to happen to that? If we split it into 2 directions, a flow of water, what happens to the concentration? Nothing. Yeah. I could pour half this water out, and whatever's in here is in both places, right? Whatever concentration of particles, it's in both places. So when we split the water, I know that's very obvious for me to say it, but keep in mind that means that the same number concentration of particles are entering each reactor. That means whatever happens in them, these are identical reactors, is going to be happening in both of them in the same exact manner. Okay? So that means we don't actually have to do anything fancy with the mass balance here, because we're solving for something about what's happening to the number of particles. We can actually just narrow our focus into one of them and recognize that's going to happen to the total. Okay? So as long as we are properly splitting the flow rate so we get our hydraulic retention time correct, then we're okay. So I'll let you take it from there. I'll be silent another few minutes and get values for K, G, and omega here, and see how you can do with the mass balance part of that. Just going to double check whether or not I have another slide for more space. Okay. All right. So carry on.
So I found G, omega,
Yep.
right? And from that I found K with respect to the initial particles.
Okay.
Okay, so that I found a K of 0.015, right? So I said the time of the reaction should be the volume over the flow rate, and I got this amount of time, and that the don't disregard this.
And that's your hydraulic residence time. That's HRT, right? Theta. Okay. And what kind of reactor are we dealing with?
Flocculation reactor.
Yeah. And what of the three that we talked about? Batch, plug flow, CSTR. Which one?
Probably a batch reactor. You have a flow in and then a reactor and a flow out.
Is this a batch reactor or a CSTR?
CSTR, because there's no inflow or outflow.
You have that backwards. Batches, no flow.
So it's going to be closer to a CSTR.
Yeah.
Okay.
So let that guide your next steps.
But, well, I guess, so disregarding the time that I found, right, I ended up, using...
We'll just label it theta, and you'll probably use it.
And then I ended up using the integrated rate law to try and find...
As if it was in a batch reactor.
Yeah.
So make sure you get clear on your mass balance. What are all your inputs, outputs? And then put in your reaction term accordingly where it belongs. Because remember, if it was just a reaction term... Yes, the mass balance. Yeah. Yes. Exactly.
I'm like, wait, I got 35 minutes. I still somehow think I got
So you're gonna want to do.
But I'm like, is that gonna be? I mean, but like, I'm wait, no, that's yes. Okay. So that's 0, right? Yeah. Okay. No, we did not want that. You gotta collapse yourself.
What's that? I haven't solved for it yet. We'll okay, great. You can proof check it a little bit. Is it larger than the initial? That's good. Is it like a crazy? Yeah.
I don't know how we're getting tonight. I don't know. That is unfortunate.
I went from 10 to the 5th particles to 0.1. It should be more particles going through here. Going through that part. Right. But something can change by word. It is an exponential.
Oh, because we only have the diameter and they just form secrets that remember. So if they're, if we know the diameter of one particle, we can figure out how many particles make up the big one. Then we know the big size.
There should be one.
I need to figure out this stack of these. Q over V, huh? So we just we divided by Q and we're left with 0 over Q. We divided that both sides. Yeah. Yeah. U over Q tension. He's talking about like end after they do. Because they have to be the same. What's the point of knowing that that's 6 happens? So then I guess if we would want to find the constant. Or maybe we just multiply at the very end. Like in the equation you would since they're identical, we would just multiply at the very end.
Like, so 10 to the 5, right? So 10 to the 5 particles per mole. That was
The volume is 50. So he must have done this. divided by less. My little phone calculator is really small.
No,
Or maybe we just maybe the way he's thinking about it is he's just talking about this one and this being and that's the reason why there should be
let's find some way to.
All right, I'm going to check in with you guys. This has actually been pretty fun seeing all the eureka moments and stuff happening here. Maybe not fun for you guys, right? Fun for me. It sounds like a lot of you are kind of getting some traction here and piecing things together, figuring out at different moments, like what's going on, why are we doing what. One thing I was noticing, so the next step for this problem would be to set up a mass balance, right? We have this reaction, we know something about the reaction. We have some reactors and know something about that. We just have to put everything together. That's where the drawing comes in, and that's why I was highlighting the fact that we can kind of isolate one reactor and pay attention to one reactor at a time to know what's happening to the particle sizes. If it's happening in one, it's happening to them both. And it doesn't really matter that they're separated. It's just the same process going through two different spots because they're in parallel like that. So in that case, I'm just going to target in my mass balance on one of them and say that the same thing that happens in that one will happen in the other one. And that'll be what we can go with. So then our N naught is entering one of the reactors. The volume for one is 3.5 cubed. That was 42.875 cubic meters. And we'll take the flow rate, the entire flow rate, and divide it in half because that's what the problem told us, right? It's split off equally into two different reactors of the same exact type. So then our Q is 1/2 MGDs. That comes out to 0.0657 cubic meters per second, given the conversion. And we'll set up a steady state problem. We weren't really given too much information about whether or not it's steady state, but it's a CSTR. We also were not talking about anything weird happening with changing over time concentrations of particles coming in. It's a pretty safe assumption to make. You could always ask me, or generally just assume it if it's, there are cases where I would either tell you it's not, or if it's a batch, you kind of know it's not. In terms of how to deal with it. So anyway, the 0, then the accumulation rate goes to 0 for across the entire thing at steady state would be Qn naught minus Qn minus Vkn. This is our decay reaction where we're putting it in. And this is why we spend all this time focusing on K. We spend a lot of work getting that K, so we know how quickly these particles are meeting, so we could put it into our mass balance term. Okay, so that means we have a mass balance term. We can go ahead and simplify, get rid of Q so that we can have theta. This is our volume over flow rate. That's just a convenient thing you could wait for later or whatever, or just put in the Q, the value there if you wanted. I just went ahead and divided by everything by Q. Then what I want here is some way to compare the initial particles to the final particles. So I could solve this like we've done before at N over N naught, and that might be useful. You might be tempted to solve to try to find N itself. I don't typically recommend that because what we actually care about is the ratio. Almost always we care about the ratio so we know how the size changed. If you have N and you do everything properly, then yeah, maybe you could go back and recalculate that and get the same number, but you're kind of doing the same math and just doing more. So I wouldn't try to solve this for N directly, rather either N over N naught, but in this case with the flocculation, it's actually more convenient to do N naught over N for exactly the reasons I was talking about here, right? because we could look at it as there are 2 new particles for every 8 old particles, or a little easier to say that 4 of the old particles in each aggregate. And that'll give us a way to compare the volumes. And once we compare the volumes, we can compare the sizes. In fact, I'm a little out of space, so I might just do it on this page. But I'll finish describing this part real quick. So if we solve for n naught over n, it's actually pretty simple. I just got the n's by themselves and divided both sides by n. So I got n plus theta kn equals n naught, just adding them to the left side. Divide everything by n, and we'll get n over n naught equals 1 plus theta k. Of course, you could leave theta as v over q. That's fine. In fact, I had to go back and calculate, okay, well, what is v over q? Because I left it in that terms. So it turns out the hydraulic retention time here is about 650 seconds, 652.6 to be exact. And that'll give us a value. And if you didn't notice, I calculated these terms here. So I put in all those for the k, found the k. Putting in that k here and this theta comes out to be 10.81 old particles for every new particle. Now, a good thing to check here is to make sure that this is a number that's more than 1. I'll come to your question in just a second. If it's not more than 1, then you are ripping particles apart somehow. And so a good proof check to yourself would be make sure this is more than 1, and you know that the physics of it kind of makes some sense. You had a question? No? Okay. All right. So with that, then we have something that we can work with to say, all right, the volume of a new particle, I'm going to call it volume of an aggregate, should be 10.81 times the volume of one of the initial particles. Okay? And if with that relationship, just simply saying volume is conserved, so the aggregates will be 10.81 times the size in terms of volume as the old ones, then we can do the calculation for the volume of a sphere and figure out the difference in diameter. So to just give ourselves a little more space, I apologize for this, but I'm going backwards 1 slide. So when you see this in the slide deck, it'll be maybe a little confusing, but I'll just write a little note. Spoilers. Okay, so the volume of an aggregate, that's 10.81 times the volume of a particle. And so we can say the volume of a particle would be, and in fact, what I'm going to do is I'm going to just use the volume of a sphere equation, right? So this would be pi diameter of the particle cubed over 6. And go ahead and put this in as, so diameter, in this case, this will be the aggregate, I'm sorry. That's what we want to solve for. Time, and that'll be equal to 10.81 times exactly the same formula, except now we're using the diameter of the particles themselves. And what you'll notice is we can simplify this pretty well. We can multiply both sides by 6 and divide both sides by pi. And essentially, we get the diameter of the aggregate cubed will equal 10.81 times the diameter of the particle cubed. So just doing the cubes here, we should be able to solve for that. I haven't done this myself yet, but I can show you what I've been working on over here. It's just doing all this in an Excel. So I'm just going to go ahead and say the diameter of the aggregate should be equal to the cubed root, and then what I'm going to do is just take this to the 1/3 power. So it should be the cubed root of, why don't I move this out of my way? 10.81 times the diameter of the particle, and in fact, I can just call back to the number here. So 10.81 times the diameter of the initial particles cubed. Let me just. Yes, thank you. That is exactly. Okay, and the reason I knew immediately that I did something wrong, thank you for the correction, is the new diameter was smaller. It was something to the negative 15th or something like that, meters, which is definitely wrong, right? So one thing you can do as you go walk through this is kind of check with yourself, hey, is this bigger? Is it smaller? Does this make sense? Is this heading in the right direction? So now we have this value, and in fact, maybe it'll be easier if I go ahead and put this into yeah, okay. We'll do this. If I put our original diameter into scientific notation as well, we see it's 1 times 10 to the minus fifth. Our new particle is now 2.2 times that size in diameter terms of. So a 10 times this volume is twice the diameter, essentially. Yeah.
We went from N naught over N equals 10.81.
Yeah.
How do we go to we add equals 10.81?
Yeah. So the question is, how did we get from N naught over N is 10.81 into some reference about the diameter of the aggregate? How does that lead into here? And the reason is, back here when we talked about the volume of each individual particle, we were going to say that the volume is conserved when they meet. So if we start with, in this example, 8 particles and we end with 2, and we're just going to say that each particle has a volume of, let's say, 1, then we have a total particle volume of 8. We still have a total particle volume of 8. And each of the new particle volumes is 4. We're just saying that when we clump 4 times 1 together, now we get 4. So that's just the relationship we're using here to say the aggregates conserve the same volume. So whatever volume that the initial ones had, now that we have 10.8 particles in each new aggregate, that's the deal.
The volume of the aggregate equals like the N naught over N times the volume of each particle.
Yeah, so that's exactly right. What I could have written is volume of the aggregate equals N naught over N times the volume of the particle. And in fact, if you do the units, you'll see that this is volume of aggregate equals the number of particles per number of aggregates times volume of particle, and the units will kind of transform into the same on both sides. Yeah.
Is it like a ratio?
Yeah, exactly. And a lot of times we'll look at the ratio as N over N naught to see like what percent are remaining. But in this case, we kind of wanted to say how many got captured, how many of the old ones are in each new one. So that's why we kind of flipped it. And a wider lesson here is like when you solve these mass balances, it's good to keep in mind what you want, right? You could have solved this for N over N naught, but then you would have had to think a little harder about how to translate that into this volume exchange, right? So that's just a matter of what you're doing for the different pieces. All right, so then our final answer, I should have written it up here while I had it. I think this was 2.2. 2.21 times 10 to the minus fifth meters. Okay, does that make sense? Good on that? Was this helpful?
So the diameter
That's good.
is smaller than the...
No, so the initial diameter was 0.01 millimeters. This should be 1.0 times 10 to the minus fifth meters. But I also had to double check, and that's part of why you saw me in here change change the units here. I was just making sure I had my calculations right. Went ahead and put that into scientific notation there. All right, well, that's good. That means we don't really have enough time to cover granular filtration today. Just as well for you, and we'll just get to that after the exam. All right, see you on Tuesday.